Hello, and welcome back to Introduction to Astronomy. In our previous segment, we were talking about Galileo and his contributions to astronomy. Well, a contemporary of Galileo was Johannes Kepler. And so he was born in 1571 and died in 1630. I don't know if he and Galileo actually ever met, but Kepler was up in Denmark at the time that Galileo was down in Italy. And Kepler was very good at plotting the positions of the planets on a piece of paper. So he got a hold of some data given by a guy by the name of Tycho Brahe. And Tycho had measured the positions of all of the planets in the night sky over many, many years. And so he had this huge amount of data, and basically on his deathbed, he gave it to Johannes Kepler. And so Johannes Kepler immediately started to plot it on a piece of paper. Now his problem, though, was that he kept trying to make the orbits of the planets around the sun circles, because he knew that the ancient Greeks thought that the circle was the most perfect kind of orbit. But try as he might, he could not get the planets to fit onto a circle around the sun. Not until he took the circle and kind of stretched it and then turned it into an ellipse. So what I'd like for you to do is get on the internet and go to the Planetary Orbit Simulator, NAAP, at UNL Astronomy. Okay, it's got a lot of fancy dials and stuff on it, but all I want you to do is just to press the play button or the start button, and I want you to observe that planet going around the sun. And you'll notice that it is an ellipse, which means that sometimes the planet is going to be closer to the sun, and then at other times it's going to be further away. So that an ellipse has two foci, or two foci, and then the sun is at one of them, and then there's nothing at the other focus. And then you can actually make an ellipse with two thumbtacks and a piece of cardboard and a piece of string. And if you attach the string to the two thumbtacks and you put it into the cardboard and then you pull it taut with your pencil, you can make the outline of an ellipse. Now you might want to take the two thumbtacks and move them closer together and see what happens. Do you notice that it's becoming more circular? And then finally, if the two thumbtacks are on top of each other, it turns into a perfect circle. So a circle actually is a special case of the ellipse. So Johannes Kepler made that his first law of planetary motion, and he said that the orbits of the planets around the sun, they are in ellipses. Okay? Then he came up with his second law of motion, that the orbits of the planets sweep out equal areas in equal amounts of time. So for this one, go back to that simulation. So go back to this simulation here, and this time click on Kepler's second law of motion. Okay, and then it's going to give you the option, it'll say Start Sweep. So press that button, and you will see that it kind of makes a triangle shaped thing. It's not actually a triangle, it's more like a sector that it makes. And then press the button again and it will make a second triangle thing. Okay, and so it looks something like this, where you've got a triangle on one side and then a triangle on the other side. They don't have to be exactly on opposite sides of the sun like it is in this picture. And then another thing that you can do is add the grid lines. And the reason for that is now you can count the number of squares that are inside each of those triangle looking things, and you'll notice that they are the same approximately. Now they should be exactly the same, but it's kind of hard to get partial boxes in there. So what's the significance of this? Okay, it's a result of the conservation of angular momentum. So we found that, let's say, for example, that here's the sun, here's the planet, and let's just say that, for the sake of argument, that this is in December. So in December, this is how far away the Earth is from the sun. Okay, now in 6 months' time, it's going to orbit over to here. Now this is greatly exaggerated. So if you're just to look at the orbit of the Earth, it really would look like a circle. But let's just pretend it's kind of exaggerated like this. So this was in December, and now this will be in January over here. Do you notice that this distance here got smaller? So we could represent this by a big R, and then over here this could be like a little r. So according to conservation of angular momentum, which is angular momentum is L, and it's equal to mv and then r. So if the r gets big, then the v has to get small in order to compensate. Okay, so over here this would have a small velocity, and then over here would be a big velocity when it's over here. Now let's say in an equal amount of time, 1 month, if you have a small velocity, you're not going to travel very far. So maybe you can only travel over to here because you're going slow. Whereas over here, you would travel a further distance because you're going faster. And so now if you find out the area of that thing there, and then you find out the area of this thing right here, you would find out that they're exactly the same. So Kepler had absolutely no idea why this was true. For that matter, he had no idea why the orbit was an ellipse. He just plotted it and found out that it was true. And similarly, he had no idea why it would sweep out equal areas in equal amounts of time, because he didn't know about conservation of angular momentum. And then he came up with his third law of motion. And what he painstakingly did was, on a piece of paper, he made graphs of time and orbital distance. So the time it would take the planet to go around, that's going to be called the period, and it's given by the letter T. So it's a Greek letter T, tau, and so I like to put hooks on it. So if you see one of these things, that means period, the amount of time it takes a planet to go around the sun, for example. If you don't see the hooks on it, then that means temperature. I know, it's confusing. Well, anyway, that's going to mean the amount of time it takes the planet to go around, and he painstakingly made graphs of the time it took to go around for each of the different planets in our solar system, and he compared that to the distance that they were from the sun, and he kept trying to make it into a straight line, because if you can make a straight line, then you can find the slope of that line, and then you can figure out what's the formula that goes with it. And so he tried various combinations, and finally he got it to straighten out by using the period squared and the distance from the sun, the semi-major axis. Now we're not going to get into what do I mean. Well, all right, you talked me into it. So here is an ellipse, okay, and then if you go all the way across, that's going to be called the major axis. If you go all the way across this way, that's going to be called the minor axis. So the semi-major axis would be the distance from here to here, and in most textbooks they call it the letter A. Okay, so getting back to my story here. He found out that the period squared is equal to the semi-major axis A cubed. Now for us, we're just going to say it's the distance from the sun, okay? Because most of these orbits really kind of look like circles, and we can just kind of take the average distance from the sun as being the semi-major axis. But to be precise, you should use the semi-major axis in these formulas. Okay, then another thing that he did was, remember, this is back in the 1600s, so he didn't know about the metric system. So he basically made up his own units. And he decided that the unit for the period was the Earth year. And then he decided that the unit for the distance was going to be this thing called an astronomical unit. Now today we actually have measured the astronomical unit, which is the distance from the Earth to the sun, and it turns out to be 1.5 times 10 to the 9th meters. So let's try it for the Earth. So how many years does it take the Earth to go around the sun? 1. Okay, so what's 1 squared? 1. All right, now how far is the sun to the Earth in astronomical units? 1. All right, so what's 1 cubed? 1. So 1 equals 1. Wow, was that exciting or what? So that shows that this formula works for the Earth. But let's see if it works for other planets in our solar system. Okay, so let's go to the next slide here. A planet is located 7 AU from a star. What is its period? So how long is it going to take this planet to go around that star if it's 7 AUs from that star? Now we're assuming that the star is the same size as the sun. We'll find out about that later. Okay, the answer is R is going to be the distance, 7. We're looking for the T, the tau. So we're going to plug into our formula. 7 times 7 times 7 is 343. But that's not the answer, because we got to take the square root of it, because we got to get the T thing by itself. So take the square root, and it turns out to be 19. Okay, but the official units that Kepler came up with were Earth years. So it would take 19 Earth years for this particular planet to orbit its star. So if you know the distance r, you can calculate the period. If you know the period, you can calculate the r thing using this. Now Kepler had absolutely no idea why this worked. He just knew that when he graphed it, it made a straight line, so that must mean that that's the formula. So again, he didn't really know what was going on. Now, if you go back to this simulation again, you can click on Kepler's third law, and you will see there's the formula, but it looks different because it's not the period squared equals to the semi-major axis cubed. You'll notice that they use the letter P instead of the period, so they say P squared, and instead of the R thing they use A, but it's still the same formula. So this formula here is the same as the one that I showed you. And so what you can do is you can change the R value and see how that changes the period, or you can change the period and see how that affects the R, and you can do the math with it and then verify it by using the simulation. Okay, so in our next segment, come on, there we go. In our next segment, we are now going to go to the time of Sir Isaac Newton and see what his contributions were to astronomy.